Hello friends, welcome back to the bench. Yes, it's time for part 2 of modding our beautiful preheater. Now, step 1 in any endeavor of modding anything is first we need to understand exactly how it works right now, or at least the parts that are relevant to us. So, this is actually very quickly. I know some of you guys reach out to me with the issues that you have or devices that aren't working and you seek help in diagnosing it. And some of you I just cannot help. All I can tell you is, because you're in front of the device, I'm not. You can do measurements and all that stuff. Yes, you can send me the pictures, but that's about it, right? You're not sending me the schematics. So step number 1, understand how the device works exactly as much as you can. Then break it into functional blocks and start pinpointing which block is not functioning correctly. In the endeavor of understanding how this works, I reversed engineered the circuitry and I put it in the simulator. Then whatever components I couldn't read or measure for one reason or another, I just introduced known or knowns into the circuit, reproduced them in the simulation, and then started playing with values of the components I couldn't match to match my observation, to match the measurements in the simulation to the observations, to the measurements in the real life. So some of the components, actually like one resistor or a couple of resistors that I introduced into the circuit, their value comes from actual measurements. So in this case, instead of our sensor, I have a potentiometer, right? But that is problem number 1. In my last video, I made an assumption that our thermal feedback is based on the thermistor. It is not. It is based on the thermocouple. Someone commented on the video saying that I'm pretty sure it's a thermocouple. Indeed, by the time I read that comment, I already knew that, because I started doing the measurements. And imagine my surprise when what I thought was a thermistor has about 2.5 ohms of resistance. Then obviously it's not a thermistor. So we're going to talk about thermistors and thermocouples in a second, and we're going to see how this circuit is built. We're going to run some measurements, and we're going to discuss how we're going to mod it. So step number 1 is our thermocoupling or a thermal feedback component, which in this case is thermocouple, not a thermistor. Depending on that, the circuit is going to be slightly different. So this is how our thermistor works. And say I ordered 10K thermistor. So this is 0K or 0 ohms actually. So we're stopping somewhere over here. So say at 200 ohms. This is our maximum temperature. So you can see that we're rising pretty linearly, right? Depending on the temperature. So this would be 5K, right? And here we have 0 degrees. Here we have around 150 degrees, around maximum temperature that the thermistor can handle. And here we have, say, 1500 degrees. Probably not. Well, the thermocouples can go as high, but this is more likely around 400 degrees over here. So our thermistor reduces the resistance the higher the temperature, relatively, at least within this region, to around, say, 120 degrees, relatively linearly. So it's relatively a simple equation, slightly adjusted, because as you can see, it's not a straight line. Slightly adjusted, but it's relatively linear. You can get pretty good accuracy. Actually, with thermistors, you get pretty good accuracy, but your range is roughly 150 degrees. Thermocouple, on the other hand, can go a lot higher, but as you can see, this is voltage or resistance. So I like to actually do it this way. So this would be voltage. So at the highest, say this is 100 millivolts. It's going to be very low potential, very low voltage. But as the temperature rises, the voltage on the thermocouple rises. Then, as you can see, it's slightly more linear in the middle here, right? So around maybe from 120 degrees to 300, maybe 250 degrees. So that is the main difference between thermocouple and thermistor. This is most important range for us because this is around 150 to maybe 250, 350. This is the range we want to work in, and this is the most linear. It is obviously not a straight line, so it definitely rises, but a lot slower. So this range over here, this might be between 8 millivolts to 20 millivolts. That's a very tiny range, while in thermistor we have pretty wide range, and to actually read the temperature based on the thermistor, all you need is the voltage divider, right? And we measure here in this junction. So the resistance drops as the temperature rises, the voltage is going to be dropping here as the temperature rises. As the temperature drops, the voltage will be going back up. So it's relatively easy to use thermistors. But to use thermocouples, the circuit needs to be a lot more advanced. So now let's take a look at the circuit that is provided in this device. So our input voltage comes here. This is AC coming straight from our transformer, 10 volts. Now we have one single diode that creates kind of a DC voltage using this big capacitor. So it's half wave rectifier. So that's why the display on this machine flickers. You can see that on the camera. You can't really see that in real life because the eye can't really catch that because it's 100 hertz, right? But the camera picks up on it, so you can see that it's blinking. Now we could modify it to make it a full bridge rectifier, and that flickering should go away. At least that's what I expect. We have a big capacitor and a 5-volt stabilizer, or the linear regulator, 7805, which in turn supplies our microcontroller with 5 volts. The next point of interest is our thermocouple, which is this connector. Now, thermocouple is amplified by this operational amplifier, and our output signal is here. This is the second output of the op-amp. It's pulled down by 12K resistor. Then from 10K resistor and capacitor, it goes to our digital input on the microcontroller. Range over here is from 0 volts to around 4 volts, which is in turn 400 degrees, if this is the highest. The highest actually is closer to 3.8 volts, but as we know, the range is not linear, so it's not like 2 volts is 200 degrees. This is probably adjusted in the microcontroller. That's why replacing thermocouple with a thermistor will not give you the good results as far as, at least as far as measurements, because if you're only using an operational amplifier as a switch to turn on, turn off, then yeah, you can replace the thermocouple with a thermistor and just adjust it to switch at the same temperature. However, for the measurement, we can't really replace them because the measurements are going to be off. Now this is our display. This is 3-segment display, and this is pretty simple. There's no data or anything like that. It's just if you route or if you push the current in one direction, one segment lights up. If you push in the other direction, the other segment lights up. This is connected directly to the outputs of our microcontroller. The outputs of the microcontroller are open collector with built-in pull-up resistor, so we can control both ground and the high signal. Now this resistor R5 is what turns on our heater. The heater is turned on when we pull this high, or which in turn opens NPN transistor, which pulls this low. The current starts flowing through our optocoupler, which in turn turns off. It turns on this switch, which is, I'm not sure, it's either a transistor or thyristor. It doesn't really bother me. It works, and I tested it. I can just put 5 volts over here and the light bulb turns on. These 2 pins is our output, which goes to the heater. This is our input. This is what powers our transformer. So these 2 pins are shorted and these 2 pins are shorted. All right. So this is just 2 connectors connecting to the input voltage, the mains. Okay, so this is the schematic I built based on the board. So it's very messy. As you can see, pull-up resistors are going down, and because once I placed the resistor, I didn't know where it goes. So I would just place it on the schematic because I found it on the board, and then tracing where it goes. So this is the cleaned up version that will be much easier to understand. The heart of this circuit is LM358, a dual operational amplifier. Now this probably would work for any other amplifier, for any other op-amp. However, since I was doing measurement on the board and I wanted to match them exactly to my schematic, to my simulation, I needed an exact part with the exact characteristics. LT-Spice doesn't come with this component, but you can find it online, you can download it, and you can import it. So that's what I did. Now, as you can see on the initial schematic, I used resistor as a thermocouple. Here I'm using a voltage source because that's more accurate. However, the measurements I do right now on the board, I'm using resistance, not voltage, because I don't really even have the ability to produce voltages this low. I'm limited to 10 millivolts and then 20 millivolts, 30, so 10 millivolt intervals. Here I would need 1 millivolt intervals, or the step of 1 millivolt. However, the circuit works the same when you apply resistance, because thermocouple also works kind of like a thermistor. However, the range of resistance is very narrow. So it starts with around 2.5, maybe 5 ohms, no, probably not even 5 ohms. And as soon as it heats up, even slightly, the resistance drops pretty much to 0. And that pretty much to 0 means that within that tiny range of milliohms, you can kind of use it as a you can measure the resistance, or your instrument can be resistance based, because as the thermocouple produces voltage, its internal resistance also changes. So the way it behaves in the circuit, it could be interpreted as resistance changing. And that is obvious by our R18, at least here, R18 on the board. It is R7. Yes, R7, which is our 6.8K pull-up resistor. Our thermocouple is coupled with with our circuit through the 200 ohm resistor, and then with both with a pull-up and the capacitor, the signal, you might say, is kind of stabilized over here. Then we just enter through the 1.5K resistor, we enter our first stage of amplification. Not much over here, negative feedback. Our output is routed directly to the non-inverting input of the second amplifier. Again, negative feedback with 12K and 10K resistor divider. 10K, and here we go to the MCU, right? So voltages on our output, so this is our output, depend on the input voltage here. So if we go to 100 millivolts, that's a very high temperature, we went to 3.5 volts, right? If we drop to 20 millivolts, we go to 60 millivolts on the output. So that's how the microcontroller knows what the temperature is. So let's see it in reality. Let's connect the input power. Our sensor shows SE, sensor issue. So let's drop the resistance to 0, and we are at 496 degrees, and our dot over here indicates, I don't know if you can see it, but the dot over here indicates that the output is on. So you can see how it changes due to my bad connection, and you can see how little resistance change have a huge impact on the reading. That's the difference between the thermistor and thermocouple. We are connected through the light bulb, so I could just make a short on these two pins, and that would light up my light bulb. But instead, I'm just gonna connect the heater. Now, when I reduce the resistance, you can see the light bulb going off. As you can see that it's a little flashy, but that's normal. That has nothing to do with the circuit. Right? So now that we understand the circuit completely, let's consider our options as far as modding it. We have several options when it comes to modding this. As you can see, we can reuse a lot of stuff from here. So our on-off switch with galvanic insulation, we can reuse that. All we have to do is just provide 5 volts to that 10K resistor, and our output will turn on. Remove that or pull it to ground, the output turns off, which means we could replace the microcontroller with perhaps Atmel, right? That gives us a lot of libraries because we can utilize Arduino. We don't have to code it ourselves. The microcontroller used on this one is S3F94C8. It's a very obscure microcontroller, probably very cheap. Pinout is relatively similar to any other microcontroller. We have 3 ports, port 0, 1, and 2, and we have several inputs, outputs. We have analog to digital converter, actually 5, 6, 7 of them. Oh, sorry, 8 of them. We can utilize 8, actually 9, because there's ADC 0 to ADC 8, so 9 digital to analog converters. So it's very handy device. We could just write new code for this one, replace it, because this one's probably already locked to the what do you call it, the production state, where you can't really read it. You can probably reset it, but it all depends on the kind of a microcontroller, right? So we could replace it with Arduino. Then for Arduino we have several options. We can utilize AD595, which basically offsets this entire circuitry that we just analyzed, can be replaced with this one IC. And what it does, as you can see, following this formula, you can calculate the temperature. As you can see, it is linear. So this is pretty much how we would read the temperature from a thermocouple. In this case, we didn't even have to import any libraries, but I'm sure there's a library that we can pull for this component to make it even easier, right? So we can replace the entire logic and use better thermocoupling and use better equipment. That would be option number 1. Option number 2 is to use a separate device, which that's what I'm gonna do, or at least that's what I'm gonna try, because I already ordered one, that will replace this entire obscure circuitry over here. And the main reason why in any case we want to get rid of this circuitry is because look at the number of elements here. Now, why is it important? As we already established, the ranges that we work in are very narrow. So to accurately measure temperature, we need a very stable device. Now, all these resistors are going to be slightly changing their values depending on the temperature. And in case you haven't noticed, this board is inside the box that heats up to very high temperatures. So obviously our temperature is not going to be stable. Our number 1 requirement is that we want a stable temperature. Number 2 requirement, we want to read the temperature of the board reliably. So we could just replace, that would be option number 3. We could just replace the thermocoupler or thermocouple with a better one, the one perhaps installed on the heatsink that we can place on the board, maybe insulated on one side to reliably grab the temperature of the board and read it correctly. Maybe instead of the heatsink, perhaps a copper element to give it some weight and give it good connection with the board. Maybe brass. That would give us much better temperature reading, but that still remains the problem of these components being unreliable still remains. We can reuse the microcontroller here as long as we match the voltage levels on the input. But based on how this device was put together, or how the what components were used and how it was used, I would deduce that the internal programming of this microcontroller is not on the world-class level. I wouldn't expect it to be wrong, plainly wrong, because as you can see, you can just copy paste the code to handle such conversion. You just need the proper equation. So I do believe that it is written correctly, but I wouldn't just want to reuse it. If anything, I would like to replace it with something else. So our modification is going to be on 2 levels. So level number 1 is electronics. We're going to replace a lot of stuff here in the electronics. The second modification is structural. So as you can see, I removed this component that went here, which surprisingly, I'm not sure, but it looks like it was glued, which is odd. This is aluminum, but you know, it's gonna work on the 400 degrees and in 400 degree conditions, so glue is probably not the best choice. I used 2 aluminum holders, brackets, I don't know what to call them. They are built from aluminum foil, actually. As you can see, it works great. Never underestimate the power of aluminum foil as a tool in the shop. It can be used for a lot of things. Second thing, this was suggested to me by the viewers. We're gonna insulate here with some high temperature insulation and close this box and just route the cables. Now the cables are going to be connected either to this, so either I'm going to reuse the output stage over here to just turn it on and off, or I'm just going to replace it entirely and just throw all this away. Maybe. But that is the plan at the moment. If you have any suggestions on a better approach, definitely drop it in the comment. I got a lot of help from you guys and after the first video, and especially my wrong assumption that it would be a thermistor, because indeed if it's inside the heater, that's not going to be a thermistor because the temperature is too high. Now we could use thermistor, and I wanted to use the thermistor and perhaps still will, because I want to heat the boards. 150 range, 0 to 150 degrees Celsius, is perfectly acceptable for this purpose. So I might still use thermistor just for better accuracy. The accuracy doesn't really come from the thermistor itself. The accuracy comes from the measuring circuit. It needs to be a lot less accurate because the 10K thermistor, which I ordered and we're gonna test it, but 10K thermistor will go from the range of 10K to maybe 500 ohms, right? That's a huge range. So we can very easily, with just one additional resistor and a digital input on the Arduino or whatever, we can measure it very reliably, very precisely. Now with thermocouple, since that range is tiny, narrow, it requires much more stable design on the electronic side, on the control side, how we actually read it. So that is the difficulty. So we need to find a sweet spot in that. So these are the modifications, and this is probably a lot more information that you ever wanted to know about how this particular device works. I was actually thrown off seeing the operational amplifier initially because of my assumption that this is the thermistor, right? Then I figured maybe, because initially I thought, yeah, it turns on and off. So the op amp is used as a switch, just turn on, off. But then it hit me that now we have actual temperature measurement on it. So no, that wouldn't work either. So that's why it took me a lot more time than it should to reverse engineer this circuit. It's very simple, and had I started with the assumption that this is thermocouple, it would have taken a lot less time. But perhaps that's why you shouldn't make assumptions right from the start. Or perhaps you should know better, Raf, that obviously it's not going to be a thermistor, right? Alrighty, that'll do. Do let me know if you have any suggestions. Thank you very much for watching. I do appreciate you. And I shall see you in the next one.